Hey guys, I just want to double check. Can everyone hear me good? Okay, great. Thank you, Tamid. All right, so welcome to the Cookies and Cram for Circuit Theory 1, ELG2138. The way I'm thinking of running this, if you guys have any better ideas for it, let me know. But the way I was thinking of going about it was first skimming through these notes, which are going to be on the Google Drive, courtesy of my good friend Valerie. This is what we used when we were taking the course. And then after that, going through an old final and just working through these questions again. That sound good to everyone? I'll also be around to answer questions after. Okay, great. So we can get started now. So a big part of the course in terms of what ends up being on the final is circuit analysis. Circuit theory, circuit analysis kind of makes sense. So here's some general definitions. I'm not going to go over most of them since they're not usually found on the circuit analysis questions, but some of them are going to be pretty important. First off, the distinction between current and voltage and where you measure them. So just keep in mind, current usually goes through a point while voltage is across 2 points. Voltage usually has a reference while current is flow. Next up, we have elements, whether they're active or passive, depends on whether they create or absorb energy. You can think of it as the active ones creating the energy, they're the ones that are active, and the passive ones simply receiving it. Moving on, we have sources, which in general are what give you a constant voltage or a constant current. If they're independent, or a dependent source, which would give you one based on the voltage or current of another element, as we'll see in one of the examples. In terms of circuit analysis, two important rules to remember are Kirchhoff's current and voltage laws, which are that the sum of all currents through a point are net zero, meaning that everything that comes in must also come out. Otherwise, it's not truly flowing and thus not current. And Kirchhoff's voltage law, meaning that around any loop, you should have a net zero voltage. A good way of thinking about that is that since you measure voltage as the difference between 2 points, if you measure voltage at the same point in a loop, you should get zero. So going all the way around that same circle should also give you zero. Moving on, we have the types of elements, resistors, capacitors, and inductors. Being sure, can you guys see the screen share? Okay, yeah, I was going through it. Let me see. Did that fix it? Okay, great. I'll just go back up a little bit. So current and voltage through area and elements, whether the element is active or passive, and sources there. So go back to where I was. Once you have resistors, capacitors, and inductors, you can have what's called a first order circuit. First order means it has only resistors and either a capacitor or an inductor, which is represented by a first order differential equation. If it has a resistor and inductor, we call it RL. If it has a resistor and capacitor, we call it an RC. Later on in this, we'll also discuss second order circuits. We also have switches in a lot of circuits as an element. They're not quite passive or active in terms that they don't create or they don't absorb energy, but they do affect the way the circuit behaves by affecting which paths can have current flow. So one more thing I'm gonna quickly cover before we get into a bit more theoretical portion is that phasors are just a representation of a sinusoid function or a periodic function, where you don't use the cosine or sine function, and instead you use the exponential form. It allows you to represent it as a complex number, which is actually easier to work with in most cases. An important part of solving any sort of analysis question is knowing how to tackle it. A good way to go about it is state your givens, figure out what you need, and then try and work from your givens to what you need. Sometimes working backwards works as well, but forwards is usually the way to go about it. Passive convention is how you read an element. And you usually look at it that the current goes from the positive to the negative terminal. If that's the case, it is the element is behaving with respect to passive convention, meaning that it's also a passive element. If the passive convention does not apply, the current is going from negative to positive of the element. When that's the case, then it's not a passive element, it's an active one, as mentioned earlier. Speaking of dependent sources, which I mentioned earlier, those are the ones that do not have a constant value and instead have an affected value. We have 4 types of those, and they're actually a permutation of current and voltage. So you can have a current controlled voltage, a voltage controlled voltage, a current controlled current, and a voltage controlled current with the following equations and the following controlling elements, signals, and constants. Let me read this off to you. I'm sure you guys are fine looking at the document after or looking at it right now. We'll just move on so we can get to the practice final sooner. Mesh analysis is a process that you can use when solving through a circuit. And it basically covers that the voltage of all of the elements is a function of the current going through the mesh. You apply Kirchhoff's voltage law to each loop, and you use the convention that the positive is clockwise to make life easier. That's the same as mesh currents, which is discussed in one of the questions. Thevenin circuits. So sometimes you want to represent a larger circuit as simply being a load and a source in order to make it a little bit easier to deal with. In order to do that, you have to cut off the load and work on it that way. So if you have an independent source, you try and find your open circuit voltage. If you have a dependent source, you try and find it through a different way, using KCL instead. Here's some examples of what the circuit would look like. So you have your open circuit voltage for your circuit. That's where you get your short circuit current, your open circuit voltage, and how you find your Thevenin resistance. You can also represent the circuit as a Norton circuit, which is similar to a Thevenin circuit, but rather than using a voltage source, Vs, you use a current source, Is. You can switch between them to help simplify a circuit using Ohm's law. So now we get to the equations portion of this, I guess, notes sheet. And it kind of covers pretty much most of the important laws. So Ohm's law, as you guys are aware, V equals IR, voltage equals current times resistance. Using that, you can use that in Thevenin circuits, use that in Norton circuits, and use it a lot in your analysis. You also have the power law, which is usually where sometimes you get the Pyre circle or the Piver circle for Pyre, where you can also relate voltage and current to power. You can also get current through capacitors or inductors through their own formulae. Voltage is very much the same way. You have Ohm's law, you have your power law, capacitor and inductor. You have for resistance and Ohms and power laws, 7 more power. For capacitance, capacitance is much like resistance, determined by physical constants. Give me a second, I can actually give you a quick bit of a diagram for the sort of where the constants come from for the capacitors. Second, things we're trying to update. Okay, there it is. Sorry about that. Okay, yeah. So for a capacitor, you can see that you have C equals epsilon A over D. So when you have a capacitor, I'm going to use a parallel plate capacitor, but this is similar for cylindrical capacitors as well. You have a wire leading up to a plate, hence the name parallel plate. You then have another plate, the other side, and then a conductor coming out the other way.
No, like the cylindrical, like the parallel one. Like, I know we don't have to understand the physical differences between the two. We use them. Like, because I know an inductor is cylindrical too.
An inductor is actually a coil of wire around a magnetic core. I'll cover that one in a second. So for the capacitor, you have these two parallel plates, usually made of a conductive material. And on the inside between them, you have something called a dielectric. So I represent dielectric. Usually it's actually a paste. So I represent it with the green in the middle here. And you have them a distance apart. So the distance between the two plates is actually your D variable for the capacitance. The dielectric that you have has a constant epsilon. And the parallel plates that you use have an area A. So your capacitance being epsilon A over D is actually the permittivity of the dielectric constant of the material, A being the cross-sectional area of the plates, and D being the distance between them. Moving on, we have, and we have the formulas to calculate the charge in a capacitor, the voltage, and the current in the capacitor. So for an inductor is similar in terms of its construction, but it's actually pretty interesting the way that they're set up. So let me get to that here. Yeah, here we are. So for the inductor, we have the wire. And just make sure that I can see the part. Okay, yeah, there we go. Oh, still another capacitor. A second. There we go. So we have a wire, and we have a, usually it's a cylindrical core.
Yes.
Yeah. Oh, you guys never covered this? Oh, this was outcome when we took the course, if I remember correctly.
It just shows you the basics and patterns of electronic components are structured.
Okay, yeah. I'm pretty sure this was an outcome. I'll just quickly skim over it. It is good to know where it comes from, especially for later courses though. Okay, excellent. So it is a ferromagnetic core that has windings of cable going around it. And that cable, that general circuit is your inductor. So you have an amount of turns, which is your N. You have the length of your winding, which is the sum of all of the turns. You have the cross-sectional area of the tube there. And then the ferromagnetic core has a property called mu. So mu, later on you're gonna, right now it's just the property of the magnetic core. Later on you learn that that's called the permeability of it, or how much magnetic fields are able to permeate through it or go through it. So an inductor, what it basically does is it converts the current into a magnetic field that's stored and then later expanded. Similar to the way a capacitor holds charge, this holds a magnetic field. So moving on from inductors and capacitors, quickly just wanted to mention, we do have the current and voltage for each. You'll notice that these are an integral and a derivative for current and voltage, but for a capacitor, the capacitor is the integral, the current is the derivative. So they're opposite in that sense. We have work or energy. Both are in this course, they're basically equivalent terms. And you can calculate the work or energy of any of these components using the following formulas. And then one of the other things that we have to cover in terms of circuit analysis is voltage and current division. These make your life way easier when you're dealing with a circuit and you don't know what the split of current or the split of voltage between series elements or parallel elements is. So for voltage division, you have that the total voltage of series elements is the sum of the voltage of each element. And if you want to find the voltage at any of those elements, it is the total series voltage times the resistance of the component you're looking for divided by the total resistance. In parallel, if you have multiple elements across from each other, all of them share the same voltage. For current, it's the other way around. In series, the current flows through all of the elements. And you can kind of think of it as sort of a pipe. If you have water coming into one end and the pipe is straight, no matter whether the pipe gets larger or smaller as you go through, the same amount of water is going to come out the other end. So the same current that came in is going to come out. Meanwhile, for current division, if you want to think of those same electrical components as pipes, if you put water through the top and you split into 4 different pipes, each one of them is going to get its own separate amount of water, or in this case, current, based on its resistance compared to the total resistance of the circuit. And resistance in parallel is additive. So if you add up all of them, you get the current that came in through the top, and you get the current that comes out through the bottom of all of them. Hold on a second. So for resistance, in series, you add them. In parallel, you add their inverses, and then you take the inverse. So that inverse sum of inverses is your parallel. For capacitors, it's the other way around. The inverse sum of inverses is your series, and the linear sum is your parallel. For inductors, it's the same as for resistors in series and in parallel. And here we can quickly touch on impedance. So impedance or impedance is more so of an idea in alternating current. And it is basically the concept that resistors, capacitors, and inductors all impede the flow of current in some way. And all of them can be expressed in ohms using a specific formula. Here you can look at a quick table that also covers inductors and capacitors with voltage, current, power, and energy. Note as well that in DC analysis, you can usually short inductors and open capacitors. It doesn't always fully work. That only happens at steady state. But at steady state, you can consider them to be a short or an open. That's because a capacitor, once it's holding all of its possible charge, it will no longer allow for current flow. And something that does not allow for current flow, by definition, is an open circuit. Meanwhile, an inductor, once it is fully charged, it is simply just a copper wire moving through, which means that it's another short circuit where a current can flow through without being impeded, or with its own real impedance, but that's not really expected here.
Very low value system.
Yes, in practice. So the maximum power theorem is something that gets touched on a little bit for the Thevenin circuits. So the maximum power delivered to a load by a source is attained when the load resistance is equal to the Thevenin resistance of the source. That's due to resistor ratios. Basically, you want to make sure that the resistor ratio of the source resistance and the load resistance are equivalent. So you can max out how much current and voltage you're putting into each. Otherwise, you end up with more current than voltage or more voltage than current, and that actually will not give you maximum power. Next up, we have switched circuits, which you guys might likely have seen. They're usually asked in sort of a question where if before zero, this is the circuit, what's the circuit after zero, and what's the circuit at steady state, or when is steady state? The way to go about those questions, first you analyze the DC before T to determine capacitor and inductor voltages. Then you recognize that they can't change. So anything before T is equal 0 is the same as T after 0 is the same as T at 0. So once you do that, you can then analyze further forwards. So back to the first and second order circuits. You can set up a Thevenin circuit with a capacitor or a Norton circuit with an inductor in order to have an easier time working with them. You can also represent them as forced response and natural response, or transient response and steady state response. In those cases, you have to consider that you can either have a constant response, in which the circuit is basically just a DC circuit, an exponential, or a sinusoid. In order to work with that, you first find the forced response before t, then you find the forced response after, and then you add the natural response to a forced response to get your complete response. So before a time constant, which you can find through capacitance or inductance, the natural response is gone, so you're in an unstable state. I'm sorry, that's after the time constant. And before that, you're in where the forced response is not there, or an unstable state. Some complete responses include having a periodic signal, having an exponential signal, or having a, sorry about that. All good? Okay, great. Or having a constant signal. You can also, in some scenarios, have a mixture of them. So for example, here we have exponential combined with sinusoidal. Moving on, we have, I'll quickly touch on this, because it's pretty important. The unit step function is simply a function that I'll give you a quick little graphing of it here. The unit step function u of t minus t naught looks like the following. If you have a t naught value here, your signal looks like this. T naught, go up, then you have the value 1, and you keep going off to infinity t-wise. So if your t naught value is 0, it's simply a function that before 0, it is 0, and after it is 1. If you look at this generic function a plus b unit, you notice that before time equals t naught, it's just a, and after it's a plus b. So simply, it is a piecewise that allows you to add or remove components. And here are some force responses to forcing functions, depending on what functions you provided. So based on whether you have an constant exponential or sinusoidal function, you can end up with the following forced responses. Remember, diagrams are important. The more you can visualize the task, usually the easier the task will be. As well, when forcing a function, if any of you are in ordinary differential equations or the numerical methods, remember that most of these forcing and forced responses are ODE concepts. You should use concepts from those whenever you can. When you don't have values in your diagrams, don't forget KCL and KVL can usually give you relationships. And if you have as many unknowns as you do functions, you can usually find them. So in the frequency domain or sinusoidal functions, you have your cosine function that is, for example, voltage equals the cosine of a period. Later on, you can convert that into a polar form. Or sorry, you can convert that into a phasor with respect to the phase shift. So I'm pretty sure that's along here somewhere. No, I'll just do that out of hand. Second of phasors. So these are a pretty important thing, and we'll touch on that in a second. Okay, no. Okay, so I'll write that down. I'll be sure to include this is the one we put in the drive after. For a phasor, if you have a function of the form, say v of t is equal to a cosine b t plus phi, if you're going to turn this into a phasor, you would simply have the phasor. We usually use a little squiggly line on top of the variable to indicate that it's a phasor. you actually end up with V equals A E to the, or sorry, A angle. And that's simply saying an amplitude of A phase shifted by that amount. As well, you can represent it as A times E to the J phi, where J is the imaginary constant. So once you have this form here, here. Great. So this form here, A angle delta, is polar form. And you can switch it to a rectangular form. A cos delta plus J A sine delta. This is to represent that phasors. And I'm not sure if you guys saw this, but it's a pretty easy way of thinking about phasors. When you have your complex numbers, but you actually have the same number on the real and imaginary plane, with a magnitude of A at an angle of delta. So if you want to turn that into rectangular coordinates, your actually, let me use a different color for the real. There we go. Your real component of A is given by a cosine theta, and your imaginary component is given by a sine of theta. Note that since it's an imaginary component, though, you have to add your nice little imaginary constant to it. And there you go. So that's sort of a more general explanation of how you can go from your polar to your rectangular. Now, what if you want to go the other way? You can simply use the tangent, the square of them. So if we had the same graph the other way, and we had a certain amount this way of real, we'll call this X. We have a certain amount of imaginary, we'll call this Y. The sum of those two, so X plus JY, would leave us here. So to find that magnitude, you would simply do the value of X squared, or sorry, wrong color, the value of X squared plus the value of Y squared, square rooted. Note that you don't square the J, you only square the Y. And that would give you your A. And to get the angle, you use good old tan. Give you that tan is, sorry, tan of delta is equal to Y over X. So the inverse tan of Y over X, see delta. As you can see here, square root of X squared plus Y squared gives you the magnitude, and the angle is given by the inverse tan of Y over X. Okay, so, and here's some other explanations of the phasors, just so that you can have a couple more identities for those. The impedances of some values, you can also find, as we saw with Ohm's law, you want to do it with AC values as well. So the impedance with respect to the period, or sorry, the periodic frequency, is equal to the voltage over current. which is the same as the magnitude with the shift of voltage over the magnitude with the shift of current. Here's a bit of a trick. If your calculator does it for you, put it in complex mode and let it take care of the angles for you. Doing phasors by hand is a pain. So if your calculator does it for you, by all means, take advantage of it. Here we cover adding and subtracting, multiplying and dividing, and the conjugate of a phasor. So the conjugate of a phasor, this is a pretty important idea because you use it sometimes to try and eliminate phasors. If you remember what the conjugate of a polynomial is, it is simply, if you have the polynomial x plus a, its conjugate would be x minus a. In this scenario, the complex conjugate, instead of having a plus JB, it has a minus JB. Do note that if this was a minus, this would be a plus. We use the conjugate symbol. If we have V of t and we want to find the conjugate of it, we use V of t with a little asterisk next to it. Why an asterisk? No clue. But yeah, that's what we use for conjugates. It's even easier if you have an angle because it's just a negative angle. The magnitude is still the same though. So for capacitors, remember if you have a polarized capacitor, you measure from the flat to the curve to measure the voltage. And to get the impedance, it's 1 over j omega c. Do note that this means that the higher your capacitance, the lower its impedance, or the higher the frequency, the lower the impedance. The current and the voltage in this case are the DC ones, and in this case are the AC ones. For the inductor, it's the other way around, actually. The higher your frequency, the higher its impedance, or the higher its inductance, the higher the impedance, as they are linear relationships. For resistors, they work the same in both. They don't really care. Moving on. Actually, I believe that's all for the notes. So if you guys want, we can get straight to the past final. I can also answer questions in between. You guys have any questions right now? Now we can just move over to that. All right, I have no questions. We can move on to the past final. All right, so this question is a state voltage question. So for these, I already have the solutions written out, but I'm going to go through the solutions and I just kind of show them, you know. We're given a source. Let me see if I can. Okay, yeah, there we go. We're given a source, Vs, of sinusoidal 5 sine 5t volts of the following components in parallel. And we want to find the steady state voltage, Vt, from this point to this point. So first, let's state all of our givens. Let's convert all of the passive components into their impedance and convert the voltage source into the cosine form. You usually want to work in cosine form. You rarely ever want to work in sine form. Do note that to convert from sine to cosine, you simply subtract 90 from the phase shift. Same thing to go the other way. So we have an amplitude of 5 with a frequency of 5 and a phase shift of negative 90. So our phasor form is going to be 5 angle negative 90 degrees or e to the negative 90j. Next up, we want to find the series inductance of the yellow branch and the blue branch, as I'm going to be referring to them. The yellow branch, we simply add in series all of the inductances. Do note that you can always add inductors in series once you already have them in their proper form. So we add their inductance here to be 8 plus 10J, and we add the blue to be 20 minus 2.4J. A handy little trick I'm sure you guys have likely seen is that if you want to convert a capacitor's inductance into not being a fraction, or at least not having the J on the bottom, you can do J omega C times J over J, which is effectively 1, which gives you J times 1 over J squared omega C. Now, the funny thing about J squared is that it's just -1. So that's the same as negative J over omega C. So that's how we get the 2.4J with the J on top. So now we try and get the voltage across the 2 Henry inductor and the 4 Henry inductor using voltage division. So we take the inductance of the element we want to take. We take the full voltage across and we divide it by the total inductance for both of them. We let the calculator do this for us because we're sure as hell not doing it by hand. And we end up with these values. So once you have those, you have the voltage from this point to this point for the 2H, and the voltage from this point to this point for the 4H. Note that for the 4H, it's actually going from here to here, the voltage we have. So this 5.68 is going from here to here. Yes, because the current flow is going this way. So we subtract the voltage of the 4H from the 2H, and we end up with this value. That's a pretty straightforward answer. Any questions on that? Give the chat a second. Why did we subtract at the end? Okay, so voltage here for these two elements, we want to measure it from the top of the 2H inductor to the bottom of the 4H inductor. Current through the 2H inductor flows with respect to the flow that we have right now for the voltage. So this one we're going to count as positive. And well, for this one, the current we found for it is going against the passive convention of the voltage that we are looking for. So we count this voltage from here to here as negative, so we can find the voltage from here to here. Does that answer your question? Excellent. Any others? Not? Okay. Yeah. Just 1 second. All right, so moving on to the next question. The circuit's steady state before the closure, determine it after for t greater than or equal to 0. Determine the voltage across this capacitor. So at t less than 0, we can see that this is open, so there's no source. This is pretty clearly at voltage equals 0, because if it had any voltage before that, it would have discharged on its own and reached 0 voltage. At voltage at t equals 0, V before 0 is as V at 0, which is 0. So we already have the at t equals 0 portion of this done. It's 0, 0. At t greater than, we reduce the rest of the circuit, close the switch, and turn the voltage source into a short circuit to find the total resistance, the Thevenin resistance, from the perspective of the capacitor, which is this branch here, 6 and 3 inverted, the sum inverted again, plus 10 in series across from this one. And then all of that in parallel with 12, giving us a Thevenin resistance of 6 ohms. Next, we find the voltage out at A and B. So we find the mesh currents. We set two currents, I1 and I2, and we perform Kirchhoff's voltage law to find voltage loops. So 6 of current 1 minus current 2, because note current 2 is traveling through the 6 ohm resistor the other way, plus 12 times current 1, plus 10 times current 1 equals 0. So net 0 voltage. And for the second loop, 6 times current 2 minus 1, since now we're looking in the direction of current 1, plus the 3 ohm resistor times current 2 equals 18 volts, since those are the ones coming from the source. Using those, we set up this system of linear equations. We plug it into our calculators from MATLAB because we're sure as hell not doing those by hand when we're timed in the exam. And we get these two currents. I1 equals half an amp, and I2 equals 7/3 of an amp. The voltage of the open circuit here, or V of this branch, is 10 times I1 plus 3 times I2, or 12 volts. Next up, we find the time constant. That's equal to the Thevenin resistance times the capacitor, or 1/4 seconds. Note that this unit is always in seconds. And we find the T then, which is going to be our V at 0 minus our open current, or sorry, our open circuit, times e to the negative t over time constant plus the open circuit, or 12 times 1 minus e to the negative 4t at t greater than 0. Do we have any questions about this one? So a little bit so you guys can see the latter portion, because the early portion is pretty simple. I see no questions in the chat.
One question.
Sorry?
Yeah, just one question. How do you know to use the exact equation for this problem?
Which one?
How do you know to use like a blue equation for this problem again?
The blue equation, great. Yeah. So this is the voltage equation for a steady state capacitor. So in the best of cases, this would be given. But if not, you can also remember that capacitors have an open circuit voltage, being the voltage that happens whether or not the capacitor is there, plus the K voltage of the capacitor. If you want, I can go a little bit more in depth about that, the K voltage, but I don't know if that's actually a circuit theory 1 topic. I think that actually gets covered more in circuit theory 2. Let me just double check if I have that in the notes. I'm pretty sure that's for next course though. It is a good question though. I also don't like just seeing random equations and being expected to remember them. Okay, yeah, so I don't see anything regarding the exponential decay of capacitor voltage. So I'm pretty sure that's a circuit theory 2 topic, but you will see this equation again. To answer your question as to sort of where the idea comes from, capacitors hold a charge and thus hold a voltage across 2 points once you charge them. And the way that they decay is actually an inverse exponential time decay based on the time constant that's given here, where they start at this voltage when time equals 0. So that plus the open circuit. And then they discharge on their own as this number approaches infinity, this approaches 0. So they discharge and all you end up with is the overcurrent. So that's sort of where the equation comes from, but it's not really something you're expecting to know for this course.
Okay, yeah, I kind of understand it. It's just I was confused with this with the first order response types of questions because I usually struggle with those. I was thinking of like how to apply that theory to this, and I just realized it's just use the formula.
Yeah. Okay. Yeah, it's not. This doesn't have to do with that. So yeah, sounds good. Okay. So for the next question, the circuit below contains a current-controlled voltage source, so a CCVS. What restriction do we place on the gain R of this source in order to guarantee that the circuit will be stable? Note that the unit step function is applied here. So we have a voltage source with the unit step function, meaning that this circuit has 2 states, before and after 0. We want to set up the circuit in order to have a load with a current. So in this case, we want to turn this load into a short circuit and find its short circuit current. So we short circuit the voltage source here, and we try and find the current traveling through there. We perform current division from here to find what the current traveling through the whole thing is. Remember that current division is the one that you're using over the sum of them times the total current. So total current here being IT. Your voltage there is going to be VT, or the voltage across this resistor, plus the voltage of this voltage source. So you're going to have the current traveling times the resistance equals the voltage total plus the current, the voltage source. And then if you solve, you find the Thevenin resistance. When you divide these two, it's going to be 400 or 500 times 400 minus R. In order to make the circuit stable, the Thevenin resistance has to be greater than 0. You determine that by finding how would you get the current to be flowing in the proper direction. You can cancel this out since you have a constant of 0 on the other side. And now what you're trying to find is what value R has to be greater or lesser than. In this scenario, R has to be less than 400. Any questions for that one? Yep. Effective gain is also called R, is not confusing. Yeah, I don't like the usage of R as a constant for gain. Later courses standardize it as K or A, and those are way nicer values for gain. A is the optimal gain variable in my opinion. I like A.
There's nothing else like apart from the unit.
You're fine.
It's not a symbol, it's a unit.
All right, if no more questions, we can move on to the next one. So we find the complex power delivered by the voltage source in the following circuit. So here we have a voltage source. We have a voltage controlled current source, and it is clearly an RC circuit because you have one capacitor and the rest are circuits. So first things first, we convert to impedance. 4 ohms is 4 ohms. 1 ohm is 1 ohm. A third of a farad becomes negative J over the frequency 2 times 1/3, or negative 3 over 2J, or 1.5. If you want to go with that. So negative 1.5 imaginary ohms of impedance. First, we take the Kirchhoff current law and we do nodal analysis at this top node. V1 over 4 minus, in this case, we're doing, this is input and this is output. So we're summing to 0. We're treating all the inputs as negative in this case. So the current going through the V1 over 4 and the current going through the voltage controlled current source, 3/4 V1, plus the output current traveling through here. Traveling through, hang on, we'll check that one. 10 minus U. Oh, okay, yeah, sorry, my bad. The voltage traveling through here over the resistance, the impedance of this entire part equals 0. So we know that the voltage at this node, just to quickly touch on that, we know that the voltage at this node is 10 minus V1, or 10 angle 0 minus V1, because we have 10 angle 0 here. We drop V1 to this node. So the voltage at this node, let me write it down. One second, yeah, switch screens here. Yeah, so the voltage at this node is equal to 10 minus V1, which is the voltage here. And you use the series summed impedance of 1 plus negative 3 over 2J as the overall impedance for this, and you end up with 0 as your sum of currents, because current in equals current out. If you isolate for V1, you try and solve, you end up with V1 equals 4 angle negative 143 degrees, which is the same as 4 angle 37 degrees. To get your current, since it's over a 4 ohm resistor, you simply divide the voltage by 4. So you get 1 with a shift of 37. And the question asked us to find the complex power. Formula for complex power is voltage times the conjugate of current over 2. So, the conjugate of the source current over 2. So the voltage of the source is 10 angle 0, since the source has no shift, as you can see here by cosine 2t plus 0 degrees, times I1, which, as you can see here, it is in series with the supply, with the voltage supply. So it is the same current, 1 angle 37 conjugated all over 2, and you end up with 5 angle 37 degrees volt amps. This one you actually could do the conjugate of just by hand, because you would just make it negative 10 over 2, 5. The angles in multiplication add, you end up with negative 37. Any questions on that one? It's a pretty straightforward problem if you can do the nodal analysis. Where does the formula come from for S? I believe it was covered in the notes that will be sent. I'm pretty sure it is. You guys did cover complex power this term, right? Oh, you might not yet have covered it. Gotcha. Okay. I'm going a little bit too fast then. Okay. Yeah, you guys are going to be ahead next week. Okay. And so the last question, last question I have for you guys. Steady state current for this mess of a circuit. It looks really messy and it looks really daunting when you first see it. But honestly, it's not actually that bad if you can follow through it. So let's look at it quickly. So we want to determine the steady state current IT going through here for the circuit shown below. So we have this current source, 20 coes, 5t plus 30 degrees milliamps. We have this parallel branch. Do note that they might be trying to trick you with here. This node right here is all one node. I don't know why it's not updating. There it is, cool. All of this, you should treat it as a single node as it is in short circuit with itself. And thus has the same current flowing through it and the same voltage from ground at that point. So you have the yellow branch and the blue branch, which is a series of inductors, or sorry, not inductors, of impedance devices. This is an RLC circuit, but it's actually not that bad of an RLC circuit. First, we turn everything into its impedance form. So the 4 turns into a 20, 10 turns into a 10 over the 10 millifarads turns into a negative 20, and so on. We just try and find all of them in ohms. And then we try and find their total single element equivalent impedance. So here we would add 40 imaginary plus 40 real plus 10 imaginary in parallel with negative 25 imaginary plus 15 real, giving us 79 angled 46 ohms. Remember, your impedance can have a phase shift. Next up, we have our yellow impedance. This was way easier. It's just negative 20 imaginary plus paralleled 20 imaginary and 20 real. Actually might have done a bit of a typo here. Let me just double check the numbers. If that's a typo, that's all right. I can just keep going from there. Just work out those numbers by hand real quick. Minus 20 plus plus 1 all inverted. Okay, so that does not work out to this, so I'll just move over here quickly. Okay, so Z blue stays the same. 5 plus 56.6. Okay. The yellow one is equal to negative 20J plus, I'm going to use this notation for the parallel components. Have you guys seen this notation? Like using, for example, resistor 1 parallel resistor 2? Oh, it's not. Okay, just give it a second. Sometimes it takes a second to refresh. Just give it a second. Oh, yeah. Have you guys seen this notation for parallel? Okay, excellent. I'll just be using that then. Okay, great. So this ends up being 20 minus 20.05 J ohms. This is ohms, which is equal to 79 angled 46 ohms. And this is equal to, just convert this. Complex, convert to the angle form. Again, if you can get your calculator to do this for you, by all means, please do it. It is so worth it. Sorry? Converting from rectangular to polar. Yes, and this ends up being 28.3 angle negative 78.7 degrees. Is there a parallel operator on the calculator? I don't think so, and it's an actual tragedy. It would be amazing if there were. I would love that. But sadly, there is not. The sum of two inverse is inverse. Yeah, it's pretty niche. Okay, yeah, so you end up with those two parallel impedances. So to find the current going through the blue branch, which is the IFT we want, we're going to do our good old current division. So current division is we want current for the blue, which means that we grab impedance for the blue. We add the impedances we add them as if they were in series. And the reason we do it is because we're looking for the ratio between the one that we took versus the ones that the other ones that we have. But do note that IFT is actually going in the opposite direction as the current from the source. So if you see, the source sends the current this way, but IFT goes in the opposite direction. So you actually need a negative. So with that, I'll just plug in the numbers. It's a little bit easier and also a little less messy. 6 divided by the answer. And this negative. Cool, and we get 2.63 minus 0.92 J amps. We get this is the ratio. We have to multiply this with the current from the source. So the current from the source is 20 angle 30 degrees. Get that number for you, 20 angle 30. That gives us a current of negative 10.11 or 0.12 minus 54.9 J milliamps. But we don't want this in rectangular. We really want this in sinusoidal. So first we turn this into polar. Again, use your calculator for this. You get 55.8 angle negative 1.7 degrees milliamps. And then all you have to do is go back to your original current source, find its frequency, 5. Now you have 55.8 cosine 5t minus 1.7 degrees milliamps. And that is your current. Any questions on that one? The entire thing was just impedance division. Pretty much, yeah. It was just current division using impedances. Yeah. Okay, no questions on this one. That's the end of the final that we had there. Do you guys have any general questions on the course or anything like that?
I guess I have a general. In high school, I did lots of different RC circuits, L circuits. The ideal RLC circuits, which are LC circuits, which are
RLC, but yeah.
No, not RLC, because they're
like a no resistor LC circuit.
Exactly.
Okay, yeah.
I'm sure you called you hearing.
Yeah, no, that would just be an LC. Yeah.
How you basically what we would do is you would be using what we call the voltage additivity law, which is similar to what we do here, which is like sometimes you get the sum of receivers or sum of passive, their voltage would be equal to the voltage of the generator. Right? And then you would use that to form a differential equation. Like your aim is just like this is what I'm talking about.
No, I know talking about.
So my question is, how helpful is this? Because it hasn't been that helpful in circuit theory one, or like knowing these, for example, understanding these. Because I remember doing this in high school.
And remembering them, not particularly.
Not remembering them, like knowing when to use them, like how to use them, still probably.
Oh, knowing when to work with first or second order circuits. It will be important if you get any sort of question asking you for the DC, not DC, sorry, asking you for the frequency response for any of those questions. But I don't think you would be asked for that for this.
No, but this like you don't know.
In electronics 1 at least, you don't really touch into that. You mostly deal with diodes and transistors.
Yes. So I studied this shit. Pretty much. It did give me some good notions that helped me.
Okay. Any other questions from anyone in the chat? Let me check. Can we do practice with FOCs with first order circuits? When do we work with time domain and frequency domain? Okay, good question for both of those. To swap between, actually both of those have a pretty similar answer to both questions. Using frequency domain for RLC circuits or for any RL or RC circuit is usually the way to go. Since it already gives you a way to look at the function without needing to use its time domain form. But if you already have the time domain form, then it's not really that big of an issue. Now, can we practice with first order circuits? Yeah, so do you have a question in particular, like a textbook question or something that you would like to go over?
Just give me the assignment.
I can't solve your assignments for you, my bad. And Angela, for your question regarding what the difference is between time and frequency domain, you use transforms to go between them, and they're basically two different representations of the same function. So, for example, yes, it's like Laplace and ODE. You usually do use Laplace for that. You can also use Fourier transforms to do the same thing in a lot of cases. It's just a general idea of not working with time and working with frequency instead.
not bad. Not too. I haven't focused on other. But if you can compress language, technically you can. We take the same person.
Yeah. So first order response. Let me switch back to the notes for that one then. So when you have a first order circuit, actually I'll draw one out here because that might make it a little bit easier. Sort of interact with it. So when you have actually I'll go over a zeroth order circuit first. If you have a voltage source with a resistor, right? Actually, hang on, that's atrocious. There we go. A little bit. Over here a little bit. Okay, so if you have a zeroth order circuit, and you measure the voltage drop for V1 with respect to time, if your voltage source, let's say it's 5 volts, right? Your graph of voltage to time is constant, right? Because since the voltage source never changes, the amount of voltage the resistor experiences never changes. In a first order circuit, however, and I'll use capacitors since they're the ones that I'm a little bit more familiar with their curve. Let's deal with an RLC. Sorry, an RL. This is the voltage we're going to be measuring. This voltage is equal to V. Just give me a second to get the formula. If anyone ever tries to tell you, you'll remember all of these by heart. They're lying to you, like an actual to your face lie. No one is going to remember all of this. Okay, 1 over C, world current. 1 over C, and then the integral from 0 to T of I T with respect to tau. I'm just make sure I put that right. Sorry, negative infinity. Okay. So you can use this one. I do like the other representation of it a little bit nicer, which is the one that's plus V naught beta. Or use the V naught after. V naught after. That's 0. So that's the voltage at that point. And let's say our voltage source is still constant. V equals 5 volts. then the curve of that VT, let's say that V0 equals 0. Then at T equals 0, you're going to have no voltage across that point. As time increases, your voltage approaches a certain point. Let me zoom out a little bit so you can see it. Using a voltage curve, you don't really have to know much about how that curve happens. You need to know is that instead of being a constant voltage, it's a changing voltage for the first order circuit. Mm-hmm. Yes.
The way I interpret it is that when the capacitor charges, it's obviously this it reaches its limit, right? So it's going to stay constant because you can't charge it over. It's like this is how I understood the concept. Like we saw this in high school. When it discharges, it's just that, or like the opposite, because it just
yeah.
You see what I mean?
Mm-hmm. Okay, yeah. So in terms of is this way the solution is K e to the negative t over tau? Yes. So I'm so glad you're getting it. So as t approaches infinity, in this case, as t approaches infinity, you can see that this flat line, right, that this line that's kind of climbing becomes flat. So as your t value gets greater and greater, this value is going to be 1 over c k e to the negative t over tau plus a v naught there. Or in this case, it's going to be a different v value, v oc. As that VOC, as this value gets larger, we just approach VOC. Same thing with the discharge. If this capacitor were to, if you were to somehow unplug the voltage source, the capacitor would then begin to discharge like this. And as time would keep approaching, you would reach 0. So that's the idea of having the first order circuit differentiated from the second order circuit. The first order circuit reaches a certain point at which it caps out, where it's at a steady state. Yeah, for constant input. What about step functions and sinusoidal voltages? Okay, great. So this example where it turns off, if this t happens to be t naught, and you have a voltage Vt equals 5u of t minus t naught, or sorry, this minus 1, this would become 5 at first. This would be 5 at t less than t naught, and 0 t greater than t naught. So this curve here is what you would see if you have a step function that was 0 up until this point. Sorry, that was 5 up until this point, and then dropped to 0 onwards. You would have that it goes up and then it discharges. For a sinusoidal voltage, and this gets closer into electronics 1 territory, where you see a voltage regulator being used with frequency. You end up with a curve that looks like this. So you start charging, and then you start discharging, and then you start charging, and then you start discharging, and then you start charging, and then you start discharging. And you can kind of see how all of this oscillates around a value with a rippling voltage. But again, that's more so an electronics 1 concept, like the idea of a sinusoidal voltage with a capacitor.
Don't worry about that.
Mm-hmm. Yeah, but I'm not teaching it.
You want to separate them? Ricky? Yeah, let's separate. Yep. Ready to suffer?
Okay, yeah, this makes sense now. Thank you.
Oh yeah, of course, no worries.
James on the way.
All right, any other questions?
Yes, is it transformer?
Yes.
Where's what you said?
Yeah, you can attend these sessions live. We were at the IEEE office. Yeah, I know, man. I know. All right, if no one has any other questions, we can stop the session here. Thank you all for coming out. If you guys have any other questions, a lot of these, the 2 documents are going to be posted on the drive. I think they already should be posted, but we'll post the updated ones that are final with the right answer on it.
That sheet with the equations. That would be really-
That's there already.
Oh, awesome.
Yeah, so the recording for the session will also be on the YouTube channel. But yeah, thanks you guys for coming.